Hi, let us now continue this basic commands, data types and function in R with the matrices in R. Matrices are this sort of a two-dimensional array of numbers, and matrices are very useful, for example, in linear regression models. If we want to calculate something by ourselves which is not easily available, then we can use just matrix algebra to come up with our new measures or test statistics. So it's obviously quite useful to understand what is the matrix, how to create a matrix, how to do simple matrix multiplication, transpose, and inverse of the matrix. So let's start with the code, example code here. So we consider first of this data type is this matrix, and we can also construct the matrices by using this sort of a function called column bind and row bind, which is kind of putting together the columns or the rows. And then we have a matrix multiplication and also the transpose and inverse of matrix is this sort of basic matrix algebra related to the matrices. But in these examples, we first use this sort of a sample function. This has nothing to do with the matrices, but it just generates the numbers from 1 to 100, in this case 12 those sort of numbers completely random. That is, all the numbers from 1 to 100 have equal opportunity to be in a sample of 12 observation. And once we have generated those sort of numbers, we can then create a matrix which could be called as A by taking those 12 numbers. And if we, for example, want to create a matrix with 4 rows and 3 columns, then we give this sort of arguments here, and we can then decide if these numbers are included into the matrix by first row or by column or row. In this case, these 12 numbers are put by row, so that the first row is first filled with these numbers, and then the second row, third row, and fourth row. If we have two matrices, let's just say A and B, then if we do this sort of a calculation, percent sign, multiplication sign, percent sign B, we get our matrix multiplication, and in this case the C, which is a outcome of this multiplication, has this sort of a structure. So obviously you can do the matrix multiplication only in the case when the columns of the matrices A is equal to the rows of matrices B. But we are not really looking here to see what are the matrix calculus itself. We assume that you are either interested or you want to learn by yourself, but this is just to introduce you to the matrices in statistics or matrices in R, and then we use matrices often in statistics. And here is, for example, example in a situation where we calculate the ordinate least squared estimate for the linear regression model. If for some reason we want to let's just say explain to see how this sort of x, which is have our values in our example now, to have these values of gender, male and females, how, for example, the y values differ in these two categories. Then we can, for example, find this sort of in a regression model, or you could call it as an analysis of variance model. In this case, how we can find this sort of a beta hat parameters by using the matrix calculus. So if we now go to the code, we can see it again, so that we can do the matrices in this way, like here. So if I take the D, A, that's a transpose. That means that the first column becomes the first row, second column becomes the second row, and third column becomes the third row. And if we think about what is, for example, if I now pick up the first row, oh sorry, let's do the matrix B2 also here so that we can have both of these things here. So and we can do the multiplication also so that we see how the matrix C looks like. So if I now take the first row of the matrix A, which I could just pick up by like this, and if I take the first column of the matrix B, which is this one, and if we now do the element-wise, this is mean element-wise multiplication, like this, and we sum. We give exactly what is here. So that's pretty much for what is in matrix multiplication going on. If we take this one, then we have taken basically the second row of the matrix R and the first column of the matrix B, and then do the same similar sort of a element-wise multiplication and sum in the end. So that's the matrices. And if we want to know then the inverse. Well, in case of if we have a C matrix, you cannot find the inverse of C matrix. But if you take, for example, transpose of C matrix multiplied by C matrix itself, let me do it again, then this matrix is a squared matrix. That means that it has the same amount of rows and columns. We can find inverse of a square matrix by using this solve function. That means the inverse of this has a value like this. So what this means, that if we take the matrix multiplication by transpose of C multiplied by C and multiplied by inverse of this matrix, that matrix is identity matrix. That means that in a diagonal there's a value 1 and everywhere else is 0. This is actually to 0, it just becomes something else to 0 because of the rounding up. So the inverse is like a in a real scalar cases, it's like a inverse number. So that's important. Where do we really need is that many times, for example, in a linear regression models, we may have if we have an X like this, then our model matrix, what we are really using in analysis looks like this, so that there's this sort of a column with the ones related to the, for example, for beta 0 vector when we go to the linear regression models, and then there could be this sort of other column which denotes is the observation male or not, in this sort of a situation when we have a X actually having the values female and male. And if we now want to see that how much, for example, the Y values are on average changing when we move to the female to male, then it really is interesting to know what this sort of a beta parameters value is, how we estimate it is to be in a case of this X male function, the column, and then we can calculate this sort of a beta hat values by using the least square estimates, and then we get this sort of a value for beta, could be called as a 1 or something like that. So this is what we have done here is to use the matrix calculus and matrices to come up with in a simple, this could be called as a linear regression model, this could be called analysis of variance type of thing, and this is actually the two-sample t-test result in the end if we want to look if the values of y are on average different level in a case of male and female. I'm not so sure if this is actually the case, that there is any difference between values in Y in categories of male and female, but at least we were able to then calculate this sort of estimate how it's on average, how much there's in average in difference. Anyway, so that was really the part of the matrices, and the second part what we should do now is to consider this sort of how we apply certain functions to the data frames. I should note that, however, that if we have this sort of, for example, biodiesel dataset, which is all but numerical one, or is it? We should look, for example, the temp here now. It's probably, yes, it's in a levels cases. So let us move this as numeric, so that we want that to be back in numeric, so that we only have a numerical values in the data set, like this way. So if I now do the, oh sorry, it already changed like this. It changed the code, so that was bad way of doing it. Anyway, so we just have to now consider that we have a bit of a bad data set here, but let's not dwell into that too much. But if I, for example, want to well, maybe I just take these three rows here. I can use these to come up with, for example, to come up with a matrix. Let's just say I call it as a Z matrix. So this would be Z matrix, for example, as matrix if I use this sort of a biodiesel, and let's take the columns of 3 to 5, like this way. So I have a Z which is now in a matrix form. So I can start doing the matrix calculus for this. Same could be obtained by using this sort of a combined function, which again should make us to the, okay, no, it's if I look the structure here, Z is now actually, is it a data frame? Yes, it's still data frame. Okay, sorry. So the combined is if you have a vectors, you can still use it as a matrix form, but if you have already data frame, then it keeps it in a data frame form. So I guess that in the end we have to really use here as matrix to come up with the same data set as in a matrix data type. So that sort of things are sometimes need to be done in order to get to jump from data being just a normal data frame to become as a matrix, because in a data frames you cannot do this sort of a matrix calculus like taking a transpose and so on. You need to somehow turn the data frame into the matrix form before you can start using the matrix calculus. But in many cases we create matrices maybe by first using these row binds and column binds, and then maybe if needed then we use the as matrix function to turn the row binds and column binds to the matrix form. So that's in practice what happens. However, we may some point use the matrices if needed. It is an important subject in statistics. In that sense, if, for example, if there's something that needs to be calculated which is not already done in some given or any functions, already written functions, and you have to calculate something by yourself, then you may need sometimes matrices. But then we can move on to the next topic, which is pretty much the last topics, that is on how to apply certain functions to the data frames. And here we have three different functions that we used in applying them to the data frames. First one is this sort of a apply function, which takes the argument. First argument needs to be the vector or the data set where we wanna apply. Then we, in a second argument, is this sort of a margin which tells us, do we want to calculate something in this data set based on the rows or based on the columns. And then comes this sort of fun argument which gives us where we should define what we want to calculate, what sort of a function we know we were going to apply to the columns or rows. And that's pretty useful. So for example, here when we have this biodiesel and we take, for example, there the last three columns, and if we now calculate column-wise sample mean, then we get sample mean of three variables. And I have used here this names function to show that we can also get our columns by using the names in these brackets. Then there's this apply function, which apply each group of values to the given each group of values given by the unique combination of levels of certain factors. So we have this sort of we need to have first of all we have a data set, or in that case we usually should have our vector. Then we have an index variable. So the index here is some variable which is kind of defining some group. So it could be either having this sort of a coded values, or it could be like having our x where we have this sort of values like male and female, and then function which we want to apply for these categories defined by this index. And here is, for example, we have used this apply for the biodiesel yield variable, and we wanted to calculate median values from this variable, but with each of these combination of time and methanol. So that's why we have calculated then take the subset of the data set from the yield belonging to the time 15 and methanol level 1, and on that subset the median value of yield values is 2.2, and similarly. And we can only have for example one value, and so on. And then the last one here is what is called an aggregate function, which is pretty much does the same things, except that we can now use this sort of it splits the data into subsets and compute a summary statistic for each. For example, here we have decided to use in aggregate function to calculate the means. That means conditional means when we are calculating from some subsets something, is it a median, mean, standard deviation, whatever we call it, that we calculate marginal distribution, conditional summaries. Conditional that some other factor or some other variable is in a certain level. And then we use the aggregate. We can then define here that which are the variables for which categories we want to calculate these sort of mean values, and in the output we have a certain categories of time and certain categories of methanol, and then what are the sample means. So these are the conditional sample means. If we change the function here for median, then we can get a conditional sample medians. If we change the function to the standard deviation, we get conditional standard deviation. So let us now go to this R code to look at how these different apply functions are working. So the first one is here that we wanna calculate on column wise from this biodiesel dataset, and from this biodiesel dataset the columns related to these variables, the sample means. So we use the function apply, then we have our dataset, and dataset is in this case selected by here, like this way. So that's our dataset. We only take these three columns, and then the argument 2 means that we calculate on column wise something, and then the function mean means that we calculate column wise the means. So this gives us the values like in this way. So the mean of methanol is this 1.5, yield is 25.77 and something, and ratio is 16.9999. If we now change here in apply function this number 1 to number 2 to 1, then we calculate with respect to the rows, that is an observation. So mean of these three numbers is equal to 1.33 and so on. And of course we can now, for example, change the function for standard deviation or just maximum or whatever we want. Or we can just later when we go to the last topics of this course, which is like a functional programming, there we also program our own functions. Then once you have done your own function, which takes like a vector as an argument, then it can calculate something there. We could try, for example, this sort of a function called summary. It then calculates mean, first quartile, median, mean, third quartile, and maximum of these variables. And this is already something what could go as an introduction to statistics with R part. So the second function here is this dapply function. Here we are interested of calculating something out of this yield, like here, but we want to now calculate with respect to the we want to calculate the median of that variable with respect to the values of these observations. So when we run this line, we get a median value of these different categories. So if I just take the one observation here, like a time, like this way, then we get this sort of a median values from yield. Or in this case, I guess we can just leave the function list out of here, like here. Or dapply if you want to calculate, for example, mean with respect to the values of x in a case of vector y, like here, then we get this sort of a mean values. Now y was like in here, and x is this giving us the gender, female and male. So that's pretty much what dapply is doing. So it gives us the chance to calculate this sort of a conditional numbers based on conditions are given by these sort of values of different variables in the list argument. And same can be obtained by using this aggregate function, like given here. It does pretty much the same thing. If we in aggregate we change for example, just for standard deviation, we get these sort of results. If we just take, for example, the factor as a methanol, then we get this sort of a result. So the standard deviation in methanol group 1 for variable yield is this much, and so on. But as you notice, here is this sort of a way of writing that which is used in a modeling in R, that we have this sort of a responsive variable y here, then comes to this sign, and then comes some explanatory variable x here. And if there's a more than one x's, like in here, we distinguish these explanatory variables by plus sign. So these both are kind of affecting the values of this responsive vector, and we calculate in categories defined by these two variables the value of the function which we are then given in these aggregate or d-apply functions. So that's pretty much for conditional calculations and apply and de-apply and aggregate functions. They are pretty useful in all the way. In different situations where we need to calculate something else. So let us now quickly still look at this example 1.3, where we need to calculate, for example, sample standard deviation of the variable weight gain. Well, that's the easiest thing to do as possible. We just take this RATS data, which we have here, as given here. And then if we just calculate the standard deviation from this variable. If you do not know what's the standard deviation, then, well, maybe we show the formula in a next lesson when we talk about the introduction to statistics, but or you can look at it in some basic of statistics course what is meant by standard deviation. But we can calculate it by using this ST function in R, so the value is like here. Then it is asked to calculate conditional sample means of the variable weight gain in different categories of this hormone variable and gender by using the double-I function. Well, we can do that similarly as we did previously, so that we take our responsive variable is a weight gain, this one, and now we calculate the sample means. So we have a function set as mean in a categories defined by these two variables, and they are put in this sort of a list object, like here. And then we use this d-apply function, which then calculates as these sort of things. Now remember, the gender now have a gender has two values. RATS gender. It has two values, like here, 1 and 2. They are codes. That's why we have two columns here in a d-apply after d-apply function, and each row is related to this hormone level variable. So the mean for case of gender P1 and this RPGH function, the variable getting the value 1, in that category the weight gain has a sample mean of 324 point something. So that's it. And then the last question is to calculate conditional sample means by variable weight gain in different categories by using the aggregate function. So do the same thing and get the same result, except that this time around we use the aggregate function. And here the idea is that you start to learn how to use these sort of formulas. They are in the underlying way of giving a statistical models to do in R, this sort of a formula as given here. And then the aggregate function is giving us the solution for this sample mean. Now the output looks a bit different, but in the end the information in this case is pretty much the same. And I could put here already some graphical thing here. So if we call this as we could put this as a data set. So if I call this as some mean values. So this is a mean values based on this aggregate. Now let me put it this way, so that I have these mean values. Now the names of the mean values are quite different. So they have, so if we have this data set like here, well, I could just give the names of the t-values, so like changing by giving the new names like RP GH as a first argument, so as a first element, then could be like a gender, like a second element, and third one could be like a mean weight, meaning that this means that the weight gains, mean of the weight gains, like this way. So if I now right here the mean values, it looks like in this way. So then I could use this sort of a function called interaction plot, where we could put, for example, these sort of variable names taken from this mean values dataset, that RPGH, then gender, and a mean weight, and the data is mean values. And if we then, oh sorry, it couldn't work that way, so we need to put here the put it in this way: mean values, gender, and a mean values, a mean weight. Otherwise it didn't quite read it. So this would now shows that how these mean values are graphically, how they are evolving in these different categories of this hormone variable and different categories of gender. So that's pretty much is our example 1.3, and is all these the apply and de-apply functions and aggregate functions. So this now sums up our functions and introduction to these basic commands and data types and functions in R, and then after this we move on to some statistics in R in the next section.